In February 2025, Microsoft stood on stage and said something that should not be said lightly. They said they had built a new state of matter. Not a faster chip, not a clever new architecture, a new state of matter, something that had never existed on Earth before their lab made it exist. And they said it was going to make quantum computing real within years, not decades. Satya Nadella himself jumped on social media and called it quantum's transistor moment, comparing this chip to the single invention that made every computer, every phone, every piece of modern technology possible. That's an enormous claim, and enormous claims in science come with an enormous responsibility to prove them. So here we are, over a year later, and in June 2026, one of the most respected scientific journals on the planet, Nature, published something Microsoft probably didn't want to see. A formal peer-reviewed critique arguing that the evidence behind their headline quantum chip doesn't actually show what Microsoft says it shows. So today, we're digging into the real question. Nobody's giving you a straight answer on, did Microsoft's quantum chip actually work? Or did one of the biggest tech companies on Earth get ahead of the science? Let's break it down. To understand why this is such a big deal, you need to understand what Microsoft was chasing in the first place, because this isn't some side project. This is a bet the company has been making for over 2 decades. Most quantum computers today, the ones being built by Google and IBM, use something called superconducting qubits. They work, but they're fragile. The tiniest vibration, the smallest temperature fluctuation, the whole calculation falls apart. That fragility is the single biggest obstacle standing between quantum computing and actually being useful for anything. Microsoft bet on a completely different approach, topological qubits, built around a theoretical particle called a Majorana zero mode, first proposed by physicist Ettore Majorana back in 1937. In theory, if you could create and control these particles, you'd get a qubit that's naturally resistant to the interference that plagues every other quantum architecture. It's a state of matter that is neither solid, liquid, nor gas, built from an engineered material stack of indium arsenide and aluminum, constructed essentially atom by atom. In February 2025, Microsoft announced they'd cracked it, the Majorana 1 chip. According to Microsoft's own account, the breakthrough wasn't just about creating these exotic particles, it was about being able to precisely measure them, using a microwave-based technique sensitive enough to detect the difference between 1 billion electrons and 1 billion and 1 electrons in a superconducting wire. That measurement is what tells the computer what quantum state a qubit is actually in. The announcement landed hard. Quantum computing stocks spiked. Senator Ted Cruz brought the chip up on the floor of the US Senate. And when Elon Musk congratulated Microsoft on X, Nadella replied with that now famous line about quantum's transistor moment. There was just one problem. A lot of physicists looked at the actual published paper and said, this doesn't prove what you're claiming it proves. The pushback didn't take months to arrive. It started within days. At a major US physics conference held shortly after the announcement, Microsoft physicist Chetan Nayak, who leads the company's quantum hardware effort, found himself facing a room described as an excited but largely skeptical, standing room only crowd of fellow scientists. The core criticism from that room was simple and damning. The Nature paper itself didn't actually detail the finished chip or provide direct proof of Majorana particles. Instead, it focused on describing a measurement method for a future device. Physicists online were, in the words of one report, outraged, posting fiery critiques, live-stream takedowns, and a wave of memes mocking the gap between the press release and the actual data. And here's the thing that made scientists especially cautious. This wasn't Microsoft's first rodeo with claims like this, and not in a good way. Back in 2018, Microsoft-backed researchers claimed they had detected evidence of Majorana zero modes. It was treated as a landmark result. Then outside, physicists dug into the data and found it didn't hold up. The paper was retracted. Nature's editors put it about as bluntly as a scientific journal ever does, stating flatly that the results in that manuscript did not represent evidence for the presence of Majorana zero modes in the reported devices. A second Microsoft-linked paper was retracted in 2021, and editors flagged possible problems in 2 others on top of that. Microsoft has maintained that those retracted papers came from outside collaborators, and that the company hadn't independently reviewed the underlying data before publication. But regardless of where the blame sits, it's a pattern. This would be the 5th Majorana-related paper to draw serious scientific scrutiny, and it's the one every subsequent claim is built on top of. So when Microsoft came back in 2025 with an even bigger announcement, a lot of the physics community's response was essentially, we've been burned by this exact claim before. Show us the receipts. Fast forward to June 24th, 2026. That's when the slow-burning scientific dispute finally landed as a formal peer-reviewed critique in Nature itself. Published in a special section, the journal reserves specifically for challenging previously published research. The author is Dr. Henry Legg, a condensed matter physicist at the University of St. Andrews in Scotland, whose entire research focus is the exact kind of semiconductor superconductor nanowire physics Microsoft's chip depends on. This isn't an outsider taking potshots. This is someone working directly in the subfield. Legg's argument centers on something called the topological gap protocol, the specific software and measurement framework Microsoft used to distinguish a genuine Majorana signal from a false positive. That protocol was the entire foundation of Microsoft's confidence. It was the tool that was supposed to filter out the noise and prove they weren't fooling themselves. According to Legg, the protocol doesn't do that job well enough. He argues the same signals Microsoft points to, the so-called zero-bias peaks in their measurements, can also be explained by much more mundane phenomena. Trivial disorder in the material, or an effect called weak anti-localization. These are well-documented sources of confusion in nanowire experiments, and critically, they can produce results that look like a Majorana signature without any actual topological physics happening at all. Legg described what he found in strikingly vivid terms. He said Microsoft had essentially claimed to have built the equivalent of a precision Swiss watch. And when he opened the case to examine the mechanism, what he found looked more like a chaotic jumble of mismatched parts. He also said the software's data analysis produced inconsistent and misreported outcomes, and that the results may have been skewed by which specific data was selected for the analysis in the first place. That's not a minor technical quibble. That's a direct challenge to whether the foundational claim, that Microsoft actually created and detected Majorana particles at all, is even supported by their own data. To their credit, Microsoft didn't dodge this one. Nature published Microsoft's formal reply alongside the critique itself, which is exactly how this process is supposed to work in real science. Critique and rebuttal, out in the open, peer-reviewed on both sides. Microsoft is standing firmly behind its research. The company describes its topological gap protocol not as flawed science, but as what it calls a practical tuning tool. Something the team already uses in day-to-day operation to configure chips before running actual quantum operations. In other words, Microsoft's position is that the protocol was never meant to be read as some kind of absolute standalone proof of Majorana particles in isolation. It's an engineering instrument, not a philosophical proof. Chetan Nayak took it a step further with a metaphor of his own, pushing back on the entire framing of the debate. He compared the skepticism to arguing about whether flight is possible while literally standing next to an airplane, his suggestion being that instead of debating the theory, critics should just come see the machine work for themselves. It's a good soundbite. Whether it settles the actual physics is a different question. Here's where the timeline gets interesting, and where you have to give Microsoft credit for either extremely good timing or extremely good instincts. Just weeks before Legg's critique landed in Nature, Microsoft unveiled a second-generation chip, Majorana 2. According to the company, this new chip can hold quantum information stable for roughly 20 seconds, about 1,000 times longer than the original version. The new chip carries 12 qubits. Now, before you get too excited by that number, 12 qubits is nowhere close to a useful quantum computer. Experts in the field are clear that a genuinely useful machine would need millions of qubits working together, not a dozen. So Majorana 2 isn't a finished product by any stretch. But if the improvement in stability is real and reproducible, it's a meaningful engineering step. Assuming, of course, that the underlying physics the whole platform depends on is actually sound in the first place. And that's exactly the assumption Legg's critique is challenging. Microsoft has publicly committed to a 2029 target for a genuinely useful quantum machine built on this architecture. That's an aggressive timeline for a technology whose foundational claim is currently being contested in the pages of the very journal that published it. You might be thinking, okay, this is a niche physics argument. Why should anyone outside a university lab care? Here's why it matters. Quantum computing is already treated as a multi-billion-dollar industry, despite the fact that genuinely useful, large-scale quantum machines don't exist anywhere yet. Investors, governments, and entire national strategies are being built around the assumption that quantum breakthroughs are imminent. When Microsoft's original 2025 announcement dropped, quantum computing stocks saw real measurable spikes. Money moved based on a press release and a paper that, according to critics, didn't even claim to contain direct proof of the core particle it was named after. That enthusiasm has cooled significantly as the scientific pushback gained visibility, and that's the real risk here. Not just for Microsoft's reputation, but for an entire industry that runs on hype cycles. If a company with Microsoft's resources, Microsoft's PR machine, and Microsoft's 2 decades of dedicated research still can't produce evidence that survives independent scientific scrutiny, it raises a harder question. How much of the quantum computing industry's current momentum is built on results that would hold up the same way? To be clear, this doesn't mean Majorana particles don't exist, or that Microsoft's entire approach is worthless. Topological qubits remain a theoretically compelling idea, specifically because they promise better error resistance than the superconducting approach Google and IBM are using. Nobody serious is saying Microsoft invented nothing. What's being disputed is much more specific. Whether the particular evidence in this particular paper actually proves what Microsoft says it proves, and whether the tool used to make that determination is trustworthy enough to build a company's entire quantum roadmap on top of. So, did it actually work? Honestly, the fair answer right now is we don't fully know, and neither does anyone shouting confidently in either direction on social media. What we do know is this: Microsoft published a paper claiming a major milestone. A specialist in the exact relevant subfield examined the data closely enough to get a formal critique through Nature's own peer review process, and concluded the evidence could be explained by ordinary, non-quantum effects. Microsoft has responded, defended its methodology, and reframed the disputed protocol as an engineering tool rather than a standalone proof. And in the meantime, the company has already moved on to a second-generation chip, while the debate over the first one is still actively unresolved in the scientific literature. That's not a scandal in the sense of fraud. Nobody credible is accusing Microsoft of faking data. But it is a real, live scientific dispute about whether one of the most hyped announcements in recent tech history actually demonstrated what it claimed to demonstrate. Given the track record, 2 previous retractions, editors flagging problems with 2 more papers, and now a formal Nature critique on paper number 5, a healthy dose of skepticism isn't unreasonable. It's just good science. The 2029 target for a working, useful quantum machine is going to be the real test. Announcements and press releases can generate stock spikes and Senate floor speeches. A working quantum computer, independently verified by outside labs, cannot be argued away with a metaphor about airplanes. Either it flies or it doesn't. That's the real state of Microsoft's quantum chip story. Not a simple, yes, it works, or no, it doesn't, but an ongoing, genuinely contested scientific debate playing out in real time in one of the most rigorous journals in the world. What do you think? Is Microsoft onto something real with the Majorana approach? Or is this another case of a tech giant getting ahead of its own science? Let me know in the comments. If you want more breakdowns like this, cutting through the hype and getting to what the actual research says, subscribe and turn on notifications, because this quantum story is nowhere near finished. Thanks for watching. I'll see you in the next one.